The pressure at Titanic's depth exceeds 5,000 pounds per square inch. Imagine stacking 50 cars on your shoulders. In 1912, divers could only reach 90 meters deep, while Titanic lay at 3,800 meters. The technological gap was so vast that finding the wreck seemed impossible. Today, remotely operated vehicles explore the Mariana Trench to 11,000 meters, nearly 3 times Titanic's depth. This revelation makes the 73-year search seem even more remarkable when you understand what early explorers were truly up against. The challenge wasn't just about locating a shipwreck. It was about conquering the most hostile environment on Earth, the impossible mathematics of 1912. When Titanic disappeared beneath the North Atlantic waves in 1912, the world's most advanced diving technology consisted of hard-hat diving suits and hand-operated air pumps. Professional divers could descend to a maximum depth of 90 meters on a good day with calm seas. Divers risked nitrogen narcosis and hours of slow decompression at just 90 meters, making any deeper work unthinkable. Titanic rested at 3,800 meters beneath the surface, creating a technological gap that seemed impossible to bridge. The wreck lay 42 times deeper than the maximum diving depth of 1912. To put this in perspective, the difference between 90 meters and 3,800 meters was equivalent to the gap between a tall building and the peak of Mount Everest. Every meter of additional depth multiplied the engineering challenges exponentially. The pressure at Titanic's depth is hundreds of times greater than at 90 meters, so existing suits and pumps would collapse. Equipment would have imploded long before reaching 3,800 meters. Crushing force at the wreck site equaled thousands of pounds per square inch, enough to compress steel and instantly destroy any diving equipment from 1912. Even if engineers had somehow solved the pressure problems, the air supply requirements would have remained insurmountable. A diver at 3,800 meters would need compressed air delivered at pressures far beyond what manual air pumps could generate. The amount of air required would have demanded industrial-scale compression equipment that didn't exist. The technological gap extended beyond just diving equipment. Navigation systems in 1912 relied on celestial observations and dead reckoning. Ships determined their position by measuring the sun and stars, methods that worked reasonably well for surface navigation but provided no way to map underwater locations precisely. Even if divers could somehow reach the wreck, they would have no way to record its exact position for future reference. Communication systems presented another impossible barrier. Surface-to-diver communication in 1912 consisted of rope signal-specific tugs on the diving line that conveyed basic messages. Complex operations required the diver to surface and discuss plans with the surface crew. At 3,800 meters, even if the diving line could reach that depth without breaking, the weight of the rope itself would make communication impossible. The search for Titanic would require solutions to problems that hadn't even been identified yet. Engineers needed to develop new materials that could withstand extreme pressure, new propulsion systems that could operate in the deep ocean, and new navigation methods that could work without reference to surface landmarks. The challenges extended far beyond simple diving technology into fundamental questions about how humans could operate in environments that seemed hostile to all life. Recovery operations would have demanded even more advanced technology. Moving or lifting a 46,000-ton ship from the ocean floor required engineering capabilities that wouldn't exist for decades. The wreck would need to be located, mapped, and analyzed before any recovery could begin. Each of these steps required technology that was completely beyond 1912 capabilities. The 73-year search timeline reflected humanity's learning curve in deep-sea exploration. Early searchers weren't just looking for a shipwreck. They were trying to solve fundamental problems in underwater technology, material science, and deep-sea navigation. The wreck remained lost not because searchers lacked determination or funding, but because the required technology simply didn't exist. Every failed expedition contributed to the knowledge base that would eventually make success possible, but that success would require inventions that were decades away from being conceived. The mathematical impossibility of reaching Titanic's depth with 1912 technology meant that any serious search would have to wait for revolutionary advances in deep-sea exploration. Yet despite these overwhelming technical barriers, the human imagination refused to accept defeat. The same period that produced these sobering calculations about pressure and depth also gave birth to a remarkable collection of ambitious schemes from inventors who believed that engineering ingenuity could overcome any obstacle, no matter how formidable the physics involved. Wild schemes and desperate dreams. These inventors approached the Titanic salvage challenge with remarkable confidence, treating the ocean floor like any other construction site. The fact that a 46,000-ton ship lay crushed under extreme pressure seemed like a minor technical detail rather than an insurmountable obstacle. In 1914, a Denver architect proposed attaching massive electromagnets to a submarine that would descend to the wreck site. The theory suggested these magnets would locate Titanic's steel hull and provide the connection point for lifting operations. Once positioned, additional electromagnets would be lowered from surface barges to winch the entire ship to the surface. The estimated cost reached $1.5 million, equivalent to $35.5 million in today's currency. The plan completely ignored fundamental problems of transmitting electrical power to 3,800 meters depth and attaching lifting devices to a hull under 6,000 pounds per square inch of pressure. The magnetic attraction plan assumed Titanic remained structurally intact and accessible for equipment attachment. The inventor never considered that the ship's steel hull would be buried under decades of sediment, making contact impossible. He also failed to account for the fact that no electrical system from 1914 could operate at such crushing depths. The plan treated deep-sea recovery like surface construction, ignoring the hostile environment that would destroy equipment long before reaching the target. Another proposal involved filling Titanic's interior with millions of ping-pong balls to create buoyancy. The theory suggested that hollow plastic balls would displace water inside the ship, making it light enough to float to the surface. Inventors calculated that approximately 27 billion ping-pong balls would be needed to offset the ship's weight. The plan called for teams of divers to carry mesh bags filled with ping-pong balls through the ship's openings, systematically filling each compartment until the vessel achieved neutral buoyancy. The ping-pong ball scheme ignored basic physics principles that would have been obvious to anyone who understood pressure differentials. The balls would collapse under pressure long before reaching the wreck. The hollow plastic shells that provided buoyancy at surface pressure would be crushed completely under deep-sea conditions. Even if the balls could somehow survive the descent, the ship's interior would be filled with debris, sediment, and twisted metal that would prevent any systematic filling operation. Numerous other ideas emerged with equal creativity and impracticality. One scheme imagined freezing the ship into an iceberg using 500,000 tons of liquid nitrogen. Other proposals suggested using 180,000 tons of molten wax pumped into the ship, training whales to attach lifting cables, or deploying giant helium balloons that would somehow maintain buoyancy under crushing pressure. Each plan demonstrated a fundamental misunderstanding of how materials behaved under extreme conditions and how objects moved through water at great depths. These schemes seemed reasonable to inventors who had never experienced deep-sea conditions firsthand. Most proposals came from architects, engineers, and businessmen whose experience with construction and manufacturing led them to believe the ocean floor was simply another work site. They applied surface-level thinking to problems that required understanding of pressure physics, material science, and deep-sea engineering. The inventors had no reference point for conditions at 3,800 meters depth because no human had ever descended anywhere near that depth and returned to describe the experience. The focus on salvage operations revealed a crucial blind spot in early thinking about the Titanic problem. Every elaborate scheme for raising the ship assumed the wreck had already been located and could be accessed for attachment of lifting devices. The inventors spent enormous energy designing systems for moving a 46,000-ton object from the ocean floor while completely ignoring the more fundamental challenge of finding that object in the first place. The salvage schemes created a false sense of progress, suggesting that finding Titanic was simply a matter of choosing the right lifting method and providing adequate funding. This misplaced confidence delayed serious search efforts for years as investors and explorers chased impossible engineering solutions instead of addressing the basic question of where the ship actually lay on the ocean floor. The coordinate problem that would plague searchers for decades was being completely overlooked while inventors focused on elaborate recovery methods. The ocean covers vast expanses, and Titanic occupied a space smaller than a city block, somewhere in that immense area. Yet the salvage dreamers proceeded as if the ship's location was already known and confirmed, when in reality the coordinates everyone trusted would prove to be dangerously misleading. The coordinate deception. The coordinates transmitted during Titanic's final distress calls created a dangerous illusion of precision that would mislead searchers for over 7 decades. When the ship's wireless operators tapped out their last desperate messages on April 15, 1912, they provided coordinates that seemed to pinpoint the exact location of the disaster. These numbers became the foundation for every search effort that followed, creating absolute confidence that searchers knew exactly where to look for the wreck. The Marconi wireless telegraph machine aboard Titanic transmitted these coordinates during the ship's final hours as the vessel listed heavily to starboard and water poured through the damaged hull. The wireless operators remained at their posts, sending out distress signals that included their position calculated using the navigation methods available in 1912. These coordinates proved essential for the rescue operation, guiding the RMS Carpathia directly to the area where survivors floated in lifeboats. The successful rescue of 705 passengers and crew members seemed to confirm the accuracy of the transmitted position. The fundamental flaw in this reasoning became apparent only decades later when searchers repeatedly failed to find any trace of the ship at the transmitted coordinates. The coordinates marked where Titanic sent its final wireless transmission, not where the vessel actually came to rest on the ocean floor. The ship continued moving for more than 2 hours after the last distress call, carried by ocean currents and its own remaining momentum as it settled deeper into the water. During these critical hours, Titanic drifted steadily away from the position recorded in its final transmission. North Atlantic currents shifted Titanic miles from its sent coordinates. The same current system that had transported the fatal iceberg also pushed the sinking ship off its transmitted course. As the ship took on water and lost propulsion, it became increasingly subject to the current's influence. The massive vessel, already listing and partially submerged, offered significant resistance to the water flow, causing it to drift substantially from its last known position. The rescue of survivors provided the first concrete evidence that the transmitted coordinates were incorrect. When the Carpathia arrived at the distressed position, the rescue ship found lifeboats and survivors scattered across an area several miles from the coordinates given in the final transmission. The lifeboats had drifted with the same current that affected the sinking ship, but their lighter weight and surface exposure made them drift even farther from the original position. The pattern of survivor locations indicated that the disaster had occurred upwind and upcurrent from the transmitted coordinates. This coordinate discrepancy created a false sense of precision that actually hindered search efforts for decades. Early salvage companies and expedition leaders focused their efforts on a small area around the transmitted coordinates, convinced that the wreck lay within a few square miles of the known position. They invested enormous resources in detailed searches of this limited area, using increasingly sophisticated equipment to examine every feature of the seafloor near the distress coordinates. When these intensive searches failed to locate any trace of the wreck, searchers concluded that their equipment was inadequate rather than questioning the fundamental accuracy of their target coordinates. Coordinates were based on last radio fixed 2 hours before sinking and ignored drift. Currents moved the ship and debris field miles off, expanding the search zone from a pinpoint to hundreds of square miles. Instead of searching a clearly defined target area, expedition teams faced the prospect of examining vast expanses of ocean floor with no clear boundaries. The expanded search area multiplied the time, cost, and complexity of any serious attempt to locate the wreck. Navigation technology in 1912 relied heavily on celestial navigation and dead reckoning methods that were prone to significant errors. Celestial navigation involved measuring the positions of stars, sun, and moon to determine a ship's location, while dead reckoning calculated position by estimating speed, direction, and time travel from a known starting point. Both methods accumulated errors over time, and factors like wind, current, and human error could easily introduce mistakes of several miles in position calculations. The officers calculating Titanic's position during the emergency would have been working under extreme stress with limited time and deteriorating conditions, making errors even more likely. The drift patterns for sinking ships created additional complications that were not understood in 1912. As Titanic settled deeper into the water, different parts of the vessel experienced varying degrees of current influence. The superstructure remaining above water acted like a sail, catching current and wind that pushed the ship in directions that could not be predicted from surface observations alone. The ship's changing buoyancy and trim as it filled with water altered its response to external forces, creating a complex drift pattern that defied simple calculation. Having coordinates proved almost worse than having no position information at all because they created false certainty that delayed recognition of the real search challenge. The coordinates suggested that finding Titanic was simply a matter of reaching the known location with adequate equipment, when in reality the first task was determining where the ship actually lay among hundreds of square miles of ocean floor. This fundamental navigation problem would require entirely new approaches that combine systematic methodology with advanced technology to overcome the decades of misdirected effort. Beasley's Dynamite gamble. By 1953, marine salvage expert Frederick Beasley had spent years studying the Titanic problem and concluded that previous search efforts had failed because they lacked systematic methodology. Traditional salvage operations relied on divers and surface equipment that couldn't reach the depths where Titanic lay, but Beasley recognized that new sonar technology offered a different approach. His marine salvage company had successfully located several shallow water wrecks using acoustic methods, and he believed these same principles could be applied to finding the world's most famous shipwreck. In 1953, Beasley dropped dynamite to generate echoes, pioneering acoustic search but lacked resolution to locate Titanic. His revolutionary approach centered on using dynamite explosions to create controlled acoustic pulses that would map the ocean floor. The theory was elegantly simple. Underwater explosions would generate sound waves that traveled through the water column at known speeds. When these sound waves struck objects on the seafloor, they would reflect back toward the surface where sonar equipment could detect and analyze the returning echoes. The acoustic mapping technique represented a significant advancement over previous search methods because it could examine vast areas of ocean floor quickly and systematically. Traditional diving operations could only investigate tiny sections of seafloor at a time, while surface-based searches relied on chance encounters with wreckage. Beasley's dynamite method could survey square miles of ocean floor in a single day, creating acoustic maps that showed every significant feature in the target area. The explosive charges would be detonated in grid patterns across the suspected wreck site, building up a comprehensive picture of the seafloor topography. Working with explosives in the rough North Atlantic waters created dangerous conditions that tested the crew's skill and courage. The dynamite charges had to be lowered to specific depths using weighted lines, then detonated by electrical signals sent from the surface. Ocean swells and unpredictable weather made handling explosives extremely hazardous, as the charges could detonate prematurely if they struck the ship's hull or if electrical systems were compromised by seawater. The crew worked in shifts around the clock, maintaining constant vigilance to ensure that safety protocols were followed during every explosive deployment. The North Atlantic's notorious weather patterns added another layer of complexity to the operation. Storms could arise suddenly, creating waves that made explosive handling impossible and forcing the team to secure their equipment until conditions improved. The cold water temperatures affected the performance of both the explosive charges and sonar equipment, requiring constant adjustments to maintain optimal operating conditions. Ice formations posed additional hazards, as floating ice could interfere with sound wave transmission and create false echoes that confused the sonar readings. During the systematic survey of the suspected wreck site, Beasley's team began detecting acoustic signatures that generated considerable excitement among the crew. Several targets produced strong echoes that suggested large metal objects resting on the seafloor. The sonar patterns indicated structures with dimensions that could match portions of the Titanic's hull or superstructure. Each promising target was carefully mapped and recorded, with multiple explosive charges detonated around the suspected objects to build detailed acoustic profiles. The acoustic analysis revealed several objects that appeared to have the angular shapes and metallic properties expected from ship components. One particularly promising target showed dimensions consistent with Titanic's massive boilers, while another displayed the elongated profile that might indicate a section of the ship's hull. The sonar readings suggested these objects were partially buried in seafloor sediment, which would be expected after 4 decades on the ocean floor. The team spent days analyzing these targets, comparing the acoustic signatures to known specifications of Titanic's construction. While innovative, the 1953 sonar blast couldn't distinguish Titanic from seabed features, so the effort failed. The disappointing reality became clear as further analysis revealed that each promising target was actually a natural seafloor feature or debris unrelated to the Titanic. Rock formations created acoustic signatures that could mimic metal structures, while other shipwrecks and debris fields produced echoes that resembled sections of the famous liner. The vast expanse of the North Atlantic seafloor contained numerous objects that could generate false positive readings on the sonar equipment. Each false target consumed valuable time and resources, demonstrating the enormous challenge of distinguishing the Titanic from the countless other objects scattered across the ocean floor. The primitive sonar equipment available in 1953 simply lacked the resolution needed to provide clear identification of targets at such extreme depths. What appeared to be promising wreckage signatures turned out to be natural geological formations or unrelated debris that had accumulated on the seafloor over decades. Beasley's expedition ultimately failed to locate the Titanic, but his acoustic mapping techniques established principles that would guide future search efforts. The systematic approach to seafloor surveying and the use of controlled explosions to generate acoustic pulses influenced later expeditions. His work demonstrated both the potential and limitations of acoustic search methods, contributing valuable knowledge to the evolving field of deep-sea exploration. The failure taught important lessons about the technological requirements for deep-sea searches and the need for more sophisticated equipment capable of operating at extreme depths. The search for Titanic would require someone willing to push deep-sea exploration technology even further. Someone with the vision to develop entirely new approaches to the challenge of finding objects in the ocean's most hostile environment. Robert Ballard arrived at the Titanic challenge in 1977 with a reputation as a marine geologist who pushed the boundaries of deep-sea exploration technology. His work at the Woods Hole Oceanographic Institution had established him as someone who thought differently about underwater operations, approaching problems with engineering solutions that other researchers hadn't considered. Ballard had spent years studying the technical requirements for reaching extreme ocean depths and understood that finding Titanic would require methods that went far beyond traditional salvage approaches. His fascination with the famous wreck had grown into a professional obsession, driving him to seek funding and develop new technology specifically for this challenge. The 1977 expedition using the Alcoa Corporation's drill ship Sea Probe ended in catastrophic failure when the drilling pipe broke, sending 3,000 feet of pipe and $600,000 worth of electronic equipment to the ocean floor. The sonar systems, cameras, and remote control claw all disappeared into the depths along with the broken pipe section. This equipment represented the most advanced underwater technology available in 1977, making its loss a significant setback for deep-sea exploration efforts. The financial impact was enormous, equivalent to over $3 million in modern currency, devastating the expedition's budget and eliminating any possibility of continuing the search. The failure provided crucial lessons about the immense challenges facing deep-sea exploration at extreme depths. The pressure and stress loads at Titanic's depth proved more destructive than engineers had calculated, revealing fundamental flaws in the design assumptions that guided the equipment development. The complexity of operating sophisticated electronic systems at such depths became apparent as multiple failure modes combined to create cascading system breakdowns. The incident demonstrated that reaching the ocean floor was only the first challenge. Maintaining reliable operations under those conditions required engineering solutions that didn't yet exist. Sea Probe's broken drilling pipe taught Ballard that heavy mechanical systems were too vulnerable for operations at 3,800 meters depth. The catastrophic equipment failure revealed that complex mechanical systems with multiple moving parts could not withstand the extreme conditions at Titanic's resting place. The drilling pipe's structural failure under pressure showed that any successful deep-sea exploration system would need to be fundamentally different from traditional salvage equipment. The loss of the remote control claw demonstrated that mechanical manipulation systems were too fragile for the harsh environment of the deep ocean floor. The equipment failure forced Ballard to completely reconsider his approach to deep-sea exploration. The traditional model of extending mechanical systems from surface vessels to the ocean floor had proven inadequate for the extreme conditions at Titanic's depth. The broken pipe and lost electronics showed that any future expedition would need to rely on simpler, more robust technology that could survive the crushing pressure and corrosive environment of the deep Atlantic. The failure taught him that success would require abandoning complex mechanical systems in favor of more reliable alternatives. Ballard's response to this expensive failure revealed the determination that would eventually lead to his success in finding the Titanic. Rather than abandoning the search, he used the experience to identify the fundamental problems that needed to be solved before another attempt could succeed. The Sea Probe disaster guided the development of his Argo system concept, which would rely on a simple underwater sled rather than complex mechanical equipment. This new approach eliminated the vulnerable drilling pipe and mechanical claw systems that had failed so catastrophically in 1977. The lost equipment became valuable knowledge that informed future expedition planning. The failure demonstrated that deep-sea exploration required entirely different engineering principles than surface operations. The extreme pressure, corrosive salt water, and complete darkness of the deep ocean created conditions that destroyed conventional equipment. Any successful system would need to be designed specifically for these hostile conditions, with redundant systems and robust construction that could withstand forces that had crushed the sea probe's sophisticated equipment. The 1977 disaster also revealed the enormous financial risks associated with deep-sea exploration. The loss of $600,000 worth of equipment in a single equipment failure showed that Titanic searches required substantial financial backing and careful risk management. Future expeditions would need to account for the possibility of total equipment loss and plan accordingly. The high cost of deep-sea technology meant that each expedition represented a significant gamble with no guarantee of success. Ballard's analysis of the equipment failure identified the need for simpler, more reliable systems that could operate independently of complex mechanical connections to the surface. The broken drilling pipe had severed all communication and control links between the surface and the underwater equipment, demonstrating the vulnerability of systems that relied on physical connections across thousands of feet of ocean. Future designs would need to incorporate autonomous operation capabilities and wireless communication systems that could function even if physical connections failed. The lessons learned from the sea probe failure would prove essential to Ballard's eventual success. But the immediate aftermath of the disaster left the Titanic search community looking for new approaches and new funding sources. The expensive failure had demonstrated both the enormous challenges and the high costs of serious deep-sea exploration efforts. The search for Titanic would require someone with both the financial resources to absorb potential losses and the willingness to take extraordinary risks in pursuit of the world's most famous shipwreck, the eccentric billionaire and his monkey. Jack Grimm represented a unique breed of Texas oil tycoon, whose vast wealth had transformed him into a professional seeker of the world's most elusive mysteries. Before setting his sights on the Titanic, Grimm had already launched expeditions to find Noah's Ark in the mountains of Turkey, searched Scottish lochs for the Loch Ness Monster, and funded teams hunting for Bigfoot in the Pacific Northwest. His approach to these legendary quests reflected the confidence of a self-made billionaire who believed that sufficient funding and determination could solve any mystery, no matter how impossible it seemed to others. The Titanic represented his most ambitious challenge yet, combining his love of adventure with a puzzle that had stumped experts for nearly 7 decades. Grimm funded his expeditions through poker game backers and a substantial gift to Columbia University for sonar equipment. His unconventional financing methods reflected his larger-than-life personality and willingness to leverage any available resource in pursuit of his goals.